Hi everybody. So today we're going to be going over chapter 2, which is titled The Chemical Context of Life. And you might be wondering why it's important that we go over these foundational concepts of chemistry when we were in a biology class. And the reason for that is because all living organisms, they are subject to the basic laws of chemistry. And not just chemistry, but also physics. And this happens because biology is a multidisciplinary science that draws insights from other courses. It is the study of life. So in our last lecture, we talked about the different ways that life can be organized into a hierarchy of structural levels. And we started off by saying that in biology, the first level is a molecule. And we mentioned that there is something smaller than a molecule, and that something is called an atom. But that we don't really discuss atoms in this hierarchy because they are more conceptually foundational to chemistry. But basically, when we have atoms, two or more atoms come together and they make a molecule. And molecules, they are eventually organized into cells. Cells are going to be organized into tissues into organs into organ systems, then into populations, into communities, and the ecosystem. And lastly, we're going to get our biosphere. But the purpose of today's lecture is to talk about this space right here. Somewhere in between the space of molecules and cells, we're going to cross a boundary, and that's when we're going to make the distinction between life and non-life. So this space, that is the space that we're going to be learning about today. Biology before we transition into the living aspect of it. And this chapter, it's divided into 4 separate sections just to make it a little bit more manageable. And the first section that we're going to go over is matter consists of chemical elements in pure form and in combinations called compounds. So to begin, we need to define matter. And matter is just defined as anything that takes up space and has mass. Therefore, all living and non-living things have matter. But what exactly is matter made up of? Well, matter is made up of elements. And elements are defined as substances that cannot be broken down to other substances by chemical reactions. And our periodic table, it is made up of 92 identified elements. And these elements, they include oxygen, hydrogen, carbon, nitrogen, and so on. And we can see these elements, which can also be called atoms, we can see them existing on their own, like we see here with these 3 oxygen atoms. And we can also refer to elements of the same type that are bonded together as pure form elements. And that's what we're seeing here with these 2 oxygen atoms bound to each other. So now that we've defined what an element is, we need to talk about a compound. And compounds, they are substances that consist of 2 or more elements in a fixed ratio. And that's exactly what we're seeing here with our 2 hydrogens to our 1 oxygen means we have H2O, and this is just water. So water is always going to have this 2-to-1 ratio. And if for some reason you see something that doesn't have this ratio, it is not going to be water. I also did just want to mention another term, which is mixture. And a mixture, it's just a combination of these elements and compounds, which are found in a solution, but they do not mix. And what I mean by that is we can find mixtures in lots of places, even including the air. But what I mean is that think about us having a beaker. And in this beaker, we have water, right? We have water, and inside of it, we dissolve table salt, which is known as NaCl. So when we dissolve this table salt into water, we now have a beaker that has water molecules and these salt molecules, and they're floating around each other. And for some reason, we want to add, let's say, iron. We want to add iron as a filler. So we do. And iron is actually denoted as Fe on the periodic table. So when we add iron to this iron molecule, it is not going to form new substances with our water molecules and our salt molecules. It's going to be separate from them. So then we're going to have salt molecules, iron molecules, water molecules. They're going to be everywhere. They're just floating around, and they do not mix, they do not create new substances. So elements and compounds, they coexist, but they do not mix to form new substances. So, like I said a moment ago, we have 92 natural elements that have been identified so far. But the thing about these 92 elements is that only about 20 to 25% of them are requirements for life. And these elements, which we call essential elements, they include oxygen, carbon, hydrogen, and nitrogen. But those are not the only elements that we need. We have 7 others that are also necessary to sustain life, even though we only need them in small amounts, and those are called trace elements. And they include calcium, phosphorus, potassium, sulfur, sodium, chlorine, and magnesium. And just because we only need them in small amounts doesn't mean that they're not important. For example, if there is a deficiency of calcium in children, they're going to get rickets. And rickets is going to cause bone deformities. Or if somebody has a deficiency of potassium, it's going to cause issues with their hearts. And that's because potassium is essential for proper muscle function and nerve transmission. So I wanted to highlight a very particular essential element, and that element is carbon. Carbon is so important to life that there is an entire field of study dedicated only to carbon, and that is organic chemistry. And the reason that carbon is so important is because carbon, it is the backbone of the complex molecules that make up our lives, like proteins, lipids, carbs, and nucleic acids. And when we're looking at our essential elements, we see that carbon makes up about 18.5% of our body mass. Meanwhile, oxygen makes up 65%. So why? Why is it that if carbon is the most important molecule, atom, that we have oxygen in more abundance in our bodies? And that's because oxygen, it's everywhere in us, because oxygen is a major component of water. And water, we know that it makes up about 60% of our body weight. And oxygen, it's also essential for cellular respiration, which is just a process that powers our cells and keeps us alive. So while carbon is critical for our structure and complexity, oxygen is what gives us energy and sustains life. So the next concept of this chapter is an element's properties depend on the structure of its atoms. So now that we've gone over some key terms, we can learn more about what an element is and the properties of an element that define it. So an element is made up of atoms. And atoms, they are the smallest unit of matter that retains the properties of an element. And although atoms are the smallest part of the element, atoms can still be broken down into subatomic particles. And so atoms, they are composed of 3 subatomic particles, and it's extremely important that you guys remember and are able to understand what these 3 particles are. And the first one that we're going to be talking about is protons. So when we look at this figure over here, we can make a few different observations about our protons, which are represented in pink. So the first one is that our protons, they are found in the center of the atom. They are found in the nucleus. And the second observation we can make is that they have a plus sign in them. So our protons, they are found in the atomic nucleus, and they yield a positive charge. So the other particle that makes up the atomic nucleus is our neutron. And they are represented in brown here. So it's also in the atomic nucleus. But something about neutrons is that they have no charge. And so we can just think of the word neutral when we think of neutrons to try and help us remember. And when we're thinking about protons, we can think about P, which stands for positive, meaning that it's always going to have a positive charge. But there is one more subatomic particle that makes up an atom, which makes up an electron, which makes up an element. And that particle is called an electron. And electrons, they have a negative charge. They are always going to be negatively charged. And they are not found inside of the nucleus. They float around in this electron cloud that we see here in yellow. And they have this negative charge. So they're found in the electron cloud, and they have a negative charge. And I want you guys to remember that atoms, they are basically just empty space with an extremely dense nucleus. And I also want you guys to remember this very important concept. The reason that atoms maintain a shape. So atoms maintain a shape because of our positively charged nucleus and our negatively charged electron cloud. These opposing charges are going to attract each other, and that's why it's going to keep a sort of shape. The positive nuclear charges of its nucleus, and the negative charges of the electron, that's what's going to keep the electrons within a certain vicinity of the nucleus. And this figure over here, it is a really overly simplified visualization of a structure of the atom. But for the purpose of this class, it's actually going to be perfect for us to use as a representation, even though it isn't the most accurate. So now that we know what an atom is, we should probably apply this knowledge to the periodic table. So when we look at the periodic table, we're going to see an element, and that element is going to contain some really important information. So the letters are going to determine what the element is. And when we're looking over here, we see Na, which stands for sodium. And in this example, we see the number 23 right here. And what this number is, it is the mass of the element. It is the mass number. And elements, they are so lightweight that using grams to specify their weights is going to get really confusing, because the weight in grams of a proton and neutron, who, by the way, they are nearly identical in weight. A weight of what composes the nucleus of our atom, it would be 10.7 times 10 to the negative 24 grams per particle. This is the weight of neutrons and protons. So if we were to take this out of scientific notation, what we would get is that we would have a 0, a decimal point, another 0, and there would be a total of 23 zeros until we got to the first number. So because of this, the unit that is associated with our protons and neutrons, the unit that we use to define the weight of an atom, it's referred to as a Dalton. And the relationship of a Dalton to a proton or neutron is this. 1 Dalton is equal to 1 neutron or 1 proton, since they are so close in weight. And something important to consider is that electrons, when we're taking the mass of an atom, they are not even considered because their weight is that much less of a proton or a neutron that it is negligible. So it's not accounted for. So going back to mass number, every single element is going to have a mass number. And the mass of an element is always going to be the sum of our protons and neutrons. And so when we're looking back over here, we see the number 11. And the number 11 is just referring to the atomic number of that element. And the atomic number tells us a lot of things. It's going to tell us the number of protons. It's going to tell us the number of electrons in a neutral atom. And the number of protons that we see in an atom is what is going to define what element it is. The number of protons will never change for sodium or any other element. If we have 11 protons, it is always going to be a sodium atom. It is always going to be a sodium element. So if we were to subtract the atomic number from the mass number, we are going to get the total number of neutrons and protons. And in this case, since we have a mass number of 23, when we subtract it from 11, we see that we have 12 neutrons. And something really important to note is that unless otherwise indicated, an atom will always have an equal number of protons and electrons. Because protons and electrons, we have them in the same quantity and they have opposite charges, this means that the atom is going to have no net charge. And another thing that I want you guys to remember is that when we're looking at the periodic table, we are not always going to necessarily see the mass number on top of the atomic number. Sometimes we see the atomic number above the mass number. But what's important to note is that the atomic number is always going to be less than mass number. So now I just wanted to go over everything that we just talked about and put it into a little chart. So we talked about subatomic particles. And the subatomic particles that we talked about are protons, neutrons, and electrons, which you can normally see denoted as an E with a superscripted minus sign. So we discussed their mass, and we said that the mass of a proton is equal to 1 Dalton, and the mass of a neutron is also equal to 1 Dalton. But we said that the mass of an electron is so negligible that we don't even count it. So, 0 Daltons. And I did just want to say that we can also talk about the mass of these particles in AMUs. And it just stands for atomic mass unit, which is the same as a Dalton. And so we also mentioned that these particles, they have different charges. So what are the charges? Well, protons, they always have a positive charge. Neutrons, they have no charge, which means they are neutral. And electrons, they will always have a negative charge. And we said that the atomic number denotes the number of protons in an element, in an atom. And this number of protons is going to be definitory for which element we are talking about. And we also discussed that the mass number, also it can be known as the atomic mass. This is always going to be equal to the weight of every proton and every neutron. So protons plus neutrons is going to be equal to our mass number, which is also known as our atomic mass. And finally, to calculate the number of neutrons, we would just have to subtract our mass number from our mass number and our atomic number. So the next thing that I wanted to talk about is an isotope. And this can be a little bit confusing. So basically, an isotope is going to refer to atoms of the same element that differ in their number of neutrons. So normally we have a 1-to-1 ratio of protons to neutrons, but when we have a different number of neutrons than we have protons, we get an isotope. And isotopes, they are naturally occurring in nature. And all this means is that one element, it can have multiple different forms. So for example, when we have our carbon isotope, we have the carbon that we see on the periodic table, which has 6 protons and 6 neutrons. It's referred to as carbon-12. However, carbon-13, which is a carbon isotope, we have 6 protons and 7 neutrons. And carbon-12 and carbon-13, they're both considered stable because they have a pretty close ratio of protons and neutrons. And these two, they do not tend to lose any particles. So what I mean by them being stable is that their nuclei, they remain intact over time. And this is different from another isotope we have, which is known as carbon-14. And it's known as carbon-14 because it has 6 protons and 8 neutrons. And this difference in the number of protons to neutrons is what's going to cause this isotope to be unstable. So because it has too many neutrons to protons, it's considered to be radioactive. And what this means is that over time, the nucleus of carbon-14, it is going to decay, and one of the neutrons that it has is going to become a proton. And because we no longer have 6 protons, we are no longer talking about carbon. We are now talking about a different atom, which is nitrogen. It is going to turn into nitrogen because nitrogen has 4 protons. And this loss of a neutron becoming a proton, it is going to make carbon-14 more stable when it becomes nitrogen. So the last concept of this energy, of this section, is energy. And basically, energy is defined as the capacity to cause change. And potential energy is the energy that matter stores because of its structure or location. It is the energy that matter possesses due to the location and structure of its electrons and atoms. So the amount of potential energy that something is going to have is based on the distance of electrons from the nucleus. So we know that electrons, they have potential energy because of their positions relative to the nucleus. So let's just say that we have carbon. And if we're going to talk about how we can describe the electron configuration of carbon, we have two energy shells. And every single energy shell, it can hold a different number of electrons. The first energy shell can hold 2 electrons, and the second energy shell can hold 8 electrons. And carbon has a total of 6 electrons. So 2 of those 6 electrons, it's going to go into the first shell, and the remaining 4 are going to fall into the second shell. And what I'm trying to say when I say that the potential energy of electrons is due to their position relative to the nucleus is that these these electrons that are inside of the first shell, they're going to have less distance from the electron to the nucleus. So they have less potential energy than the electrons that we find in the second shell. So because there's less space between an atom's first shell electrons to its second shell electrons, that is what we're talking about, potential energy. The greater the distance between an electron and the nucleus, the greater the potential energy of that atom. So matter, it has a natural tendency to move towards the lowest possible state of potential energy. And in biological systems, our molecules, they're going to tend to break down into more simple forms. And this breakdown is going to release energy, which is going to cause it to move towards a more stable state. So now we're going to get more into detail of the idea of energy levels of electrons. So, like I said before, electrons, they float around the nucleus of an electron in a cloud, and that cloud can also be referred to as a shell. And we can think of every single shell as an energy level. And I did say that defining an atom structure by its shells is an oversimplified model. So I need you guys to please keep in mind that electrons, they do not perfectly surround the nucleus like how we're seeing here in this carbon. We do not see them perfectly orbiting around here and perfectly orbiting around here. They are somewhere within this electron cloud. And actually, we can never know exactly where an electron is, but we can determine the location probability of this electron. But for now, we are going to continue forward with the idea of energy levels. So every single atom, it is going to have a certain amount of energy levels, which are the circles that surround the atom's nucleus. And on each level, we are going to find our electrons. And no matter the element, each energy level, it can only hold a certain amount of electrons. So when we're looking at this carbon atom, what we see is that it has 6 electrons. 1, 2, 3, 4, 5, 6. So carbon has 6 electrons, which is also its atomic number. So what we know is that the atomic number tells us the number of protons in the nucleus, which is what's going to define an atom, and that unless otherwise stated, we are always going to have the same number of electrons and protons. So we have 6 protons and 6 electrons in a carbon atom. So therefore, this atom, it is neutrally charged. And when we subtract our atomic number from our mass number, which is 12, we get 6. So when we look at this chart over here, what we see is that the first shell, it can hold only 2 electrons. The second can hold 8 electrons, and the third shell can hold up to 18 electrons. We can form more energy shells, but for the scope of this class, knowing how many electrons can be held in the first 3 shells is all that matters. So since carbon has 6 electrons, and 2 of those electrons go into the first shell, we have only 4 electrons left that can go into the second shell. But because the second shell can hold up to 8 electrons, our shell is not complete. So I wanted to go back to the idea of potential energy. In the first shell, we have a shorter distance from electron to nucleus, and in the second shell, we have a greater distance from electron to nucleus. And this increased distance, it's what's going to increase that potential energy of the electron. And because matter always wants to move to the lowest possible state of potential energy, this is why atoms, they can actually donate or gain electrons. In the case of carbon, carbon does not usually donate electrons. It is usually going to share electrons to complete its outermost shell. And the outermost shell and the outermost electrons, they are referred to as the valence shell and the valence electrons. And I also wanted to mention that when elements interact with each other, it is the electrons that are involved. The nucleus is never going to be involved. So we said that the valence electrons in the valence shell is referring to the outermost electrons in the outermost shell. Which brings us to why the valency of an atom is so important. Well, when the valence shell of an atom is full, that atom is considered stable and unreactive. So when we look at our carbon atom, do we think it was stable? No, it's not, because the valence shell of carbon can hold up to 8 electrons, but it only has 4. And the number of valence electrons that an atom has is going to determine how an atom interacts with others. So going back to our carbon, the last thing I said was that if carbon comes in contact with another atom, it can donate all of its elements. And this donation is going to make carbon more stable because now it's moved to a lower energy state. It has a complete valence and it has less potential energy. However, because carbon has 4 valence electrons, it is more likely to form covalent bonds with other elements. And forming these covalent bonds is going to make carbon more stable. So the next section of this chapter is the formation and function of molecules depend on the chemical bonding between atoms. So chemical bonds are just the interactions between atoms which causes them to stay together. And these chemical bonds, they are created when atoms have incomplete valence shells, when they share or transfer their valence electrons with other atoms. And the bonds that can come from these interactions include covalent bonds, ionic bonds, hydrogen bonds, and van der Waals forces. And something important to note is that covalent and ionic bonds, they are intramolecular forces. And hydrogen bonds and van der Waals forces, they are intermolecular forces. Intramolecular meaning that it occurs within the molecule. and intermolecular, meaning that it occurs between molecules. So now we're going to talk about covalent bonds. So a covalent bond is formed when a pair of valence electrons is shared by two atoms. So when we're thinking about carbon, we know that carbon has an incomplete valence shell, and we know that carbon is more likely to share its electrons with other atoms to complete its outer shell than it is to donate them. And this sharing of electrons is what's going to lead to covalent bonds, which is going to allow carbon to be a more stable atom, a more stable element. So one of the atoms that carbon forms covalent bonds with is hydrogen. And this is because hydrogen only has one electron. So when we're looking at the electron configuration of hydrogen, it has one electron, so it has only one energy shell. And when we're looking at the electron configuration of carbon, it has two shells with 2 electrons in the first shell and 4 electrons in the second shell. So what happens is that when we have 4 hydrogens available, they're going to form covalent bonds with carbon. And what's going to happen is that suddenly we're going to have a hydrogen here, a hydrogen here, a hydrogen here, and here. And this is going to create a molecule which is known as CH4, which is known as methane. And I also wanted to mention that when 2 or more atoms are held together by covalent bonds, that is when a paired elements are considered molecules. So remember that pure form substances are 2 or more bonded substances of the same element. So just because it is 2 or more atoms does not always make it a molecule. For something to be considered a molecule, it must be covalently bonded. And another concept that I wanted to bring up is that atoms, they do not always equally share electrons. So an atom that pulls an electrons closer to itself is always going to be more electronegative. And electronegativity is defined as an atom's attraction for the electrons in a covalent bond. And how electronegative an atom is can be determined by the periodic table. For example, when we move up a periodic table this way, we increase in our electronegativity, and when we move from left to right on the periodic table, we also have an increase in electronegativity. So now that we know a little bit about electronegativity, we need to talk about covalent bonds and the different kinds of covalent bonds that there are. So covalent bonds, they can either be polar or nonpolar. And when electrons in a covalent bond are shared equally, they are called nonpolar covalent bonds. And a few points I want to make is that covalent bonds between 2 atoms of the same element is always nonpolar. A covalent bond between atoms with similar electronegativities is also going to be nonpolar. So nonpolar is equal to similar electronegativities, and it's also equal to atoms of the same element being bonded. So same element. And in the example that we see here, we see carbon and we see hydrogens. And carbon and hydrogen, they have very similar electronegativities, which is what we're seeing here, 2.1 and 2.5. And because of these similar electronegativities, the bonds are nonpolar because they are not sharing, neither of these atoms is going to pull the electrons closer to each other, which is why we have a nonpolar covalent bond. But on the other hand, we have polar covalent bonds. And polar covalent bonds occur when two atoms, when they have a great difference in their electronegativity. And this is what causes them to not share the electrons equally and form these polar covalent bonds. So when we look at a water molecule, we see that there is 2 hydrogens and 1 water molecule. And oxygen, it has an electronegativity of 3.5. Meanwhile, hydrogens are 2.1. So the difference in electronegativity is 1.4. And this is enough that it's going to be considered a polar covalent bond. So because oxygen is more electronegative, it is going to pull the hydrogen's atoms closer to itself. And that's also going to give it regions of partial negative charges. So our oxygen atom, it is going to have a charge that is partially negative, which is denoted this way. And our hydrogens, they are going to be partially positive. And this is because the electrons are now closer to oxygen, so there are more electrons than protons in this oxygen atom, giving it that overall negative charge. And basically, bonds, they're just classified as polar and nonpolar depending on the difference of their electronegativity. And we can actually mathematically calculate it, which is when this chart is actually going to come in handy. But this is out of the scope of our class, so please don't memorize any of these values. But basically, mathematically, a bond is considered a polar when its electronegativity ranges from 0.5 to 1.7. And nonpolar is considered when the difference in electronegativity is less than 0.5. And anything greater than 1.7 is going to be considered an ionic bond, which is what we're going to talk about next. So now we have to talk about ionic bonds. And ionic bonds form when two atoms are so unequal in their attraction to valence electrons that one atom essentially steals an electron from the other. And the more electronegative atom, the one that wants electrons more, it's going to take the valence electron from the less electronegative atom. So, for example, we have our NaCl molecule, which is table salt, and our sodium, when we look at its electron configuration, we see that it has one valence electron, because sodium is going to have 2 electrons in its second shell. It's going to have a complete second shell, meaning that it has 8 electrons in its second shell, and in its third shell, it's going to have only 1 electron. And sodium and chlorine, on the other hand, chlorine is going to have 2 electrons in its first shell, 8 in its second shell, and in its third shell, chlorine is going to have 7 valence electrons. 6 and 7. So when we check the electronegativity values of chlorine, we can see that even when we're looking only at the periodic trends, chlorine is much more electronegative than our sodium ion. It has an electronegativity of 3, meanwhile sodium has an electronegativity of 9. And what happens is that this chlorine atom, it's going to want sodium's valence electron so badly that it's going to take it. So this this electron here is just going to leave sodium and it's going to go directly to chlorine. So now chlorine is going to have 8 electrons in its valence shell. And the concept of an atom having 8 electrons in its valence is called the octet rule. And all the octet rule states is that atoms have a tendency to want 8 electrons in its valence. So, because chlorine is so much more electronegative, it's going to pull sodium's single valence electron, and it's going to complete its valence shell with 8 electrons, which leaves sodium's outer shell empty. And after this transfer, because sodium lost an electron, it became a positively charged cation. And cations, they always have a positive charge because now the sodium has more protons than electrons. And because chlorine gained an electron, it's going to be called an anion. And it's always going to be negatively charged because it's now going to have more electrons than protons. And this transferring of electrons is what gives our atoms a charge, which is why we see it as Na plus and Cl minus. And the difference in charge creates an attraction between the positive sodium ion and the negative chloride ion, which is what forms an ionic bond. And one more thing, compounds that are formed by ionic bonds, they are called ionic compounds or salts. And NaCl is an example of a salt or an ionic compound. And it's also important to note, like I said before, ionic bonds and covalent bonds are intramolecular, meaning that they hold atoms together within a molecule. And covalent and ionic bonds, they are also the 2 strongest types of bonds that we have. So now we need to talk about our hydrogen bonds and van der Waals forces. So hydrogen bonds, they form when a hydrogen atom that is already covalently bonded to one electronegative atom is attracted to another electronegative atom. So what this means is that we have this hydrogen molecule atom right here, and it's attracted to this more electronegative oxygen. And because there are other water molecules floating around this one, this hydrogen atom that's already attached to this oxygen is going to have an attraction to this oxygen, which is found on a different molecule. So, hydrogen bonds, they form a polar covalent bond because these polar covalent bonds, because these hydrogen bonds, they leave the hydrogen atom with a partial positive charge and the other atom with a partial negative charge, which is what we see here, a partially positive charge and a partially negative charge. And the partially positive charged hydrogen, that is going to be attracted to the regions of full or partial negative charges on molecules, atoms, or even regions of the same large molecule. So molecules or atoms that are close together, they can attract each other due to temporary charge differences. And these weak attractions, they are known as van der Waals forces. And van der Waals interactions, they allow for atoms and molecules to stick together for a short period of time. So overall, when it comes to bonds, although individual bonds are temporary and they are individually weak, collectively they are strong and play a very important role in biology. And the cumulative effect of individual bonds is to reinforce that three-dimensional shape of a large molecule. So now we're just going to talk about how the shape of a molecule helps to determine its function. So something fundamental to biology is that form always follows function. And the shape of a molecule is going to be a determinant of its function within a cell. And a molecule that has two atoms is always going to be linear. However, most molecules that have more than two atoms, they have a more complex shape. And the shape of these molecules, it's determined by the positions of the regions where electrons are most likely to be found. It's called the orbitals. So when atoms bond, their orbitals, they actually overlap and they merge to form shared spaces for these electrons. And the arrangements of these orbitals is going to determine the overall shape of the molecule. I do not want you guys to worry at all about learning all these kinds of orbitals. It's out of the scope of this class. We don't need to know it. But what we need to know is that the different orbitals that we have, they have different three-dimensional shapes. And this figure is just so that you guys can kind of see that the different kinds of orbitals, that they have different dimensions to them. And those dimensions, they're going to influence the structure of the molecule. So moving on to the last section of this chapter, we have chemical reactions make and break chemical bonds. So chemical reactions are the making and breaking of chemical bonds. And in chemical reactions, when chemical bonds are broken and reformed, it leads to new arrangements of atoms. And I want you guys to remember that when a bond is broken, there is a release of energy. And when a bond is created, energy is absorbed. And this is because breaking a bond requires energy input to overcome the attraction that is found between the atoms. Meanwhile, forming a bond is going to release energy because the atom becomes more stable. So an important term to know is reactants. And reactants are just the starting molecules of a chemical reaction. And on the other hand, we have products. And products are the resulting molecules of a chemical reaction. And all chemical reactions, they must be balanced. And what this means is that the number of atoms of each element on the reactant side has to be the same as the number of atoms on the product's side. And this is going to follow, it's always going to follow that law of conservation of mass, which states that matter cannot be created and it cannot be destroyed. It can only be transformed. So in this example, we see that we have hydrogen on our reactant side and we have oxygen. When we do the math, we see that we have two hydrogens and we have to multiply it by this 2 here. So we have a total of 4 hydrogens. And here we see that we only have 2 oxygens. So on the reactant side, we have 4 hydrogens and 2 oxygens. And when we look at the product side, we see that we're always going to have the same atoms and that we're going to have the same number of atoms on the product side that we had on our reactant side. So again, when we do the math, we see we have 2 hydrogens and we multiply it by a 2 there, which we get 4. And when we put this 2 and we multiply it by our lone oxygen, we see that we have 2 oxygen atoms. So the products and reactants, they have the same number of atoms on each side. And a great example of chemical reactions is photosynthesis. So photosynthesis is so important to us because humans and other animals, ultimately, we depend on photosynthesis for food and oxygen. And like I said in the last slide, reactions are always going to follow the law of conservation of mass, which states that energy cannot be created or destroyed, only rearranged due to an energy input. And in the case of photosynthesis, our energy input is sunlight. So when we look at the reactants and we do the math, we see that we're going to have 6 carbons, 12 oxygens in carbon dioxide. We're going to have 12 hydrogens and 6 oxygens in water. So when we put that together, we get a total of 6 carbons, 18 oxygens, and 12 hydrogens. And when we look at our product side, we see that we have in glucose 6 carbons, 12 hydrogens, and 6 oxygens. And when we look at our oxygen molecule, we're going to have 12 oxygens total. So even though we have different formulas, we're still going to have the same number of atoms in the reactants and our product side. So we have 6 carbons, 18 oxygens, and 12 hydrogens in our product side, which is the same thing that we had on our reactant side. So eventually, the rate of formation of products is going to be equal to the rate of breakdown of products. And when that happens, the system is at chemical equilibrium. And at equilibrium, products and reactants, they are continually being formed, but there is no net change in the concentrations of reactants and products.